Thank you very much. And okay, so should I start now?
Yes.
Okay, so welcome to my presentation about counting distinct patterns in internal dictionary matching. My name is Juliusz Staszyński. Oh, can I actually see it on the right, or can you see actually yourself on Zoom? Because it's covered by Zoom on my screen.
I can see myself. You can
Okay, I have hidden this. All right. So let's say we have some patterns. These are displayed as various colors, and we have a text. This is displayed as a straight white line. And there are some occurrences of those patterns at this text. They are indicated by appropriate arcs. And we have some kind of queries. We have queries on some interval. And we would like to know how many different colors are completely encompassed. So there is some full occurrence at this interval. So for example, in this case, it's 2 because there is a yellow arc and then there is a blue arc. So there is a blue occurrence and there is a yellow occurrence. And when we push the interval to the left, the answer is still 2 because while one full blue occurrence have been added, it doesn't change the answer because we count only distinct patterns at the query. So if we push the query interval to the right until it encompasses fully the orange interval, then the answer will become 3. So to sum up, we would like to count all distinct patterns occurrences at some interval. Okay, and now the spin-off is when we consider internal dictionary matching, when each of the patterns is actually some substring of the text. So the information needed to represent the pattern is constant for all of the patterns. And okay, so let's fix some numbers. We fix D as patterns count and N as the text length. And you can note that the sum of the lengths of the patterns, despite the information being linear size, can be, let's say, quadratic. It is text length multiplied by patterns count. Okay, so let's go to some background. Why would we even consider this? So this is a natural extension of internal pattern matching. In the case of internal pattern matching, we have only one pattern that we are supposed to look for in the text. In the case of the internal dictionary matching, the patterns are many, but the information about them, so we can say that internal pattern matching is basically batch matching of some interval. So Keller et al. Had an internal pattern matching solution, which had sublogarithmic query and required nearly linear space. And of course, later there is a Kosciuszka paper, celebrated Kosciuszka paper, where we had a constant query, linear space, but the limitation here is that the size of the query should be more or less equal to the size of the pattern. And then we have internal dictionary matching, which is an extension of this problem of the internal pattern matching. And it started with, not start, but there were several results in the internal dictionary matching work by Karampopoulos et al. At Isaac. And we improve upon those results. Basically one result, because those first 4 queries had similar performance. The size was polylogarithmic. Note that O with tilde means that there is a hidden logarithmic factor, and it will reoccur at the presentation, at many places at the presentation. So the query time was constant, forgetting about logarithmic factor, and the size was linear. So that's pretty good. But in the case of count distinct, they had some logarithmic query time, and we improve upon this by presenting several results. All right. So let's look at our results. We have 4 kinds of results. Most interesting of them are the first and the fourth one. I mean, most interesting algorithmically. The first is two approximation, and we have achieved this by having constant query time and small space and preprocessing time. And this will be the main point of this presentation, to show that algorithm and prove how it works. We also have presented a trade-off. So you can see that there is an M here. So N is obviously N is length of a text, and M is an arbitrary parameter. For example, if we fixed M as a square root of N, we could get here the same space as in the first row, preprocessing time the same as the first row, and the query time square root of N. So every time we asked, for a query, we would answer it in roughly square root of N time. But we can fix any parameter here, and we would have gotten different performance trade-off. Finally, we have considered a special case when the dictionary is all squares occurring in the text. And this is interesting because when you consider runs, that is well, basically squares are the most basic forms of periodicity. It's just a repetition. So this gives some kind of information about the interval we are querying, about how much of periodicity we need to consider there. Well, it is something that we would like to know, and we have used several tricks to get this query time. All right. So let me present you the proof of the true approximation variant. So let's start with some basics. So we all know, okay, maybe no, we don't, but there is a popular MOSE algorithm, and the MOSE algorithm requires that we preprocess some large intervals, and then to get the answer for exact interval queries by extending to the right or the left the information that we have gotten from preprocessed interval. And we do something literally like this in the case of the trade-off solution, but here it will be a little bit different. So let's say that somebody has told us about the answer for some query. So some magic fairy has told us about what is the answer for count distinct at ij. And now we would like to extend this interval to the left or to the right, or maybe contract it, and get the answer for the larger interval or smaller interval. So the interval changes slightly, and we would like to know how the answer changes. So let us see what actually happens here. So these blue boxes are occurrences that have that have been added by extending this interval to the left. And those are all prefixes at this I-1. Some of them already occurred in this green interval before, and some of them are new. So note that this is monotonic. So we would like to find actually a cutoff point. So because basically you can see that if a pattern occurs, if pattern occurs in the green text, all shorter patterns also occur in the green text, because these are all prefixes of the I-1. So basically, we need to find a cutoff point that will allow us to know how many new pattern occurrences we have there. So let us take advantage of the fact that all of them lie on the same path at the suffix tree. So this is some kind of suffix tree path, and we have marked some nodes, which are words, which are patterns from the dictionary. And this is where bounded SCP queries will help us. And let us see how they look, and we will see how they help us. So we are given a single text and two fragments of that text. So basically two intervals. And bounded SCP queries allow us to get the longest prefix of U that also occurs at V. Yes, so we actually extend maximally in the U until we cannot find anything this pattern in V. So let us return to the original problem. So how does this help us? So this actually provides us with a cutoff point directly, and we need only to count nodes that are dictionary patterns that are below this tree, this cutoff point. And this is easily achievable by preprocessing the suffix tree in such a way that every node holds how many dictionary nodes are on the way to root, basically on the way to root from it. So for each node, not necessarily dictionary node, we hold how many dots are above it, and then to find the answer, we get the result from here, and we like to remove dots that appear above here. And to find the cutoff point that we have computed using our bounded SCP queries, we will use weighted ancestor queries, which allow us to jump up to the tree in sub-logarithmic time. All right. So now we are able to. I have shown you the way how to contract an interval query or extend interval query left to the right, because everything is symmetric. And we will look how to exploit this actually. So we could contract our interval from the left and extend it to the right. Then we would get something like a sliding window. And this, if we fix some length, we can we can basically use the sliding window to compute the result for all substrings of a fixed length. And we'll do that for all powers of some length. So this is something like a base factor decomposition, but a bit more dense. a bit more dense because we require some more because we require some more factor. Okay. And when we ask for a query, we can actually ask for the prefix and the suffix. I mean, unless the delta is bigger than 1, but we will not care about that. So we have preprocessed it for some lengths. When we get a query, we can always find such intervals that they go like this. So what are we lacking? This is almost a true approximation, but we still need information from those patterns that start on the left and end on the right. And this is how we do this. So we have we have the case that we would like to count all dictionary patterns that occur starting from F1 and ending on F3, but don't occur in any of these yellow intervals, because we would like to. Then we will count them even more than we should. All right. So we divide, as always, it into two cases, where the pattern is periodic, and by periodic I always mean highly periodic, so it consists of at least, so it's longer than 4 occurrences of periods. And then we can deduce that the required patterns occur at most once, because otherwise P wouldn't be periodic. Why? Because the overlap is too great. So note that here we have F1 smaller than 1/8 of F2. So if there is some occurrence that starts in F1 and ends in F3, then it will be long enough to have a large overlap in the middle. So then we know that P occurs at most once in this case. If we know that it occurs at most once, instead of thinking how it can be done, we can just use what we already have. We can use just simple count. So we don't count distinct occurrences, but we count all occurrences. And after some thinking, it can be shown as correct, actually. Okay. So the second case is P is periodic. Then what we have is that we can deduce that the middle is actually also periodic, and we can extend the periodicity to the left and to the right maximally. And then we would have a run. And then we get a somewhat similar evaluation. We need to subtract, we need to get some periodic occurrences and subtract some other. And notice that all periodic strings can be uniquely identified by fixing this Lindon root, having this left and right tail length of them. And then we could generate from these 4 free numbers and 1 word the entire periodic string. So we get some kind of inequalities which give us conditions when one string contains another string, and these conditions are equivalent in 2D interpretations to some rectangles. So we can achieve this, and if we can achieve this, then we can answer the solution exactly. And if we can get this information exactly, we actually have 2 approximation. And we have 2 approximation in this query time. Well, we have the required results. So this is one part of the paper that I wanted to present to you, and I invite you to take a look at our paper because the tricks there are pretty nice. So thank you for your attention, and yeah, thank you for your attention.